Hello everyone, I'm Shengong Yang from National Tsinghua University from Taiwan. I'm glad to be here to present our paper Flow-Based Intrinsic Curiosity Module to you. I'll first go through the summary of our paper and followed by the motivation. Then I'm going to introduce the architecture of our proposed method in this highlight video. The summary of our paper are listed as follows. First one, we propose FICM for evaluating the novelty of observations. FICM generates intrinsic rewards by using the prediction errors of optical flow estimation to encourage the DRO agent to explore unfamiliar motion features. And second, we compared FICM against a number of baselines and validated that FICM is capable of focusing on the motion features and will guide the agent for exploration. The last one, we presented a set of ablation analysis to investigate the impact of FICM to the agents. And here is the motivation. You can see a video in the slide, a cat is playing ball out of its curiosity. So this inspired me, which I think that the motion of unfamiliar patterns appearing in the view would arouse the people or animals' curiosity. And the second important thing is that I think that the rapidly changing part or moving patterns between two consecutive frames can always be interpreted as important signals. This means that we can encourage the RL agent to learn the motion features in the environment. So here we need to design a new exploration bonus method that is able to understand the motion features between observations, and also we need to encode the observation efficiently. And the last one, but the most important thing is that the method must able to estimate the novelty of different observations. So we try to embrace optical flow estimation and propose flow-based intrinsic curiosity module, which we also called FICM. Then here's the overview of the proposed framework. The idea here is really simple. Suppose we have two consecutive observations, then we can feed these observations into a flow predictor G, and then we can just predict a pair of optical flow in different directions. One is backward flow, and then we can use the predicted flow with a wrapping operation to get the predicted output. Once we get the predicted output, then we can calculate the loss using this predicted output and the original input to get the loss in a self-supervised manner. And the most special thing here is that the loss is directly served as the intrinsic reward signal. This means that high intrinsic reward means the agent is unfamiliar with the motion, so the flow prediction will not be that good. And the low intrinsic reward means that the agent saw the motion before, so the flow predictor can predict the optical flow well. In order to validate the quantification and properties of FICM, we need to know the prediction error is monotonically decreased as time passes by, so the RO agent will get less rewards as the time passes by. And from this image, we can see that it yields higher intrinsic rewards for unfamiliar observations than familiar ones. So here is some visualization of the impact of FICM. So you can see the attention areas of the trained agent is aligned with the prediction error from flow predictor. And this means that intuitively, our agent will learn the motion features and focus on the moving part in the environment. This is the end of the highlight video of this paper, and thank you for your listening. Welcome to our poster if you are interested in this topic.